This is the fifth video of a series on vectors. The first three videos looked at vectors in 2 dimensions, establishing rules for component form, magnitude, and adding and subtracting vectors and multiplying by a scalar. The same rules will apply to vectors in 3 dimensions. The last video looked at coordinates in 3 dimensions, and this video will look at vectors in 3 dimensions. So when dealing with 2-dimensional vectors, we added vectors head to tail. We added vectors by adding the components. If we multiplied a vector by a number, a scalar, then we multiplied the components by that number. And if we wanted the size of the vector, its magnitude, we took the component form, squared the components, added them, and took the square root. That followed from Pythagoras' theorem. What was done with vectors in 2 dimensions, all these rules apply to 3 dimensions. It's just there'll be a third component. So there's an x component, there's a y component, and in 3 dimensions there's a z component. So just like coordinates had x, y, and z coordinates in the last video, we've got x components, y components, and z components to the vectors. We plotted points on a set of axes that were at right angles to each other. So if we plotted 4, 2, 6 to depict that as best we could, here's a set of x, y, and z axes. There would be 4, 2, 6. 4 on the x, 2 on the y, and 6 on the z. So that's 4 along here on the x-axis, and at right angles to that, into the board, 2 on the y-axis, and vertically, so at right angles again, 6 on the z-axis. 4, 2, 6. Another example here is 4, 2, negative 6. So that would be 4 on the x, 2 on the y, and here negative 6 on the z means 6 down. Or here's negative 4, negative 2, 6. So that's negative 4 on the x, negative 2 on the y, and 6 on the z, and so on. That was in the last video. Also, when working in 2 dimensions, if we wanted, using coordinates, directed line segment AB here, we would look at the x coordinate being negative 1, becoming 7, and that would require an addition of 8. So you need to add 8 to the x coordinates. That would make the x component of the vector 8. The y coordinates be changed from 2 to 6, so it has to gain 4. That's the y component of the vector is 4. So for directed line segment AB, it's column vector 8, 4. Put 8 onto the x coordinate, negative 1, give it an extra 8, it becomes 7. And the y coordinate 2 gains this 4 to become 6. So this says add 8 onto the x coordinate and 4 onto the y coordinate of point A to get you to point B. Then the magnitude, the size of the vector AB is, and the directed line segment AB is, square the components, add and take the square root. If it's a surd that simplifies, simplify it. Separate video for surds. Here to go from C to D, negative 2 is becoming 5, so the x coordinate has to go up by 7. And the y coordinate is going from 4 to 3, so the y coordinate has lost 1. So as a directed line segment CD, as a column vector here, add 7 onto the x and negative 1 onto the y coordinate of C. Negative 2, add 7 is 5. Y coordinate 4, add that negative 1 gives you 3. So it's 7 onto the x coordinate, negative 1 onto the y coordinate of C to get to D. Magnitude of directed line segment CD is square the components, add and take the square root. 7 squared, negative 1 squared, 49, and positive 1 makes root 50, which will simplify to 5 root 2. The length of that line is 5 root 2 units. So that was all done in the first video. Component form, 2 dimensions, x and y. Size of the vector, the magnitude, square the components, add and take the square root. So we apply that in 3 dimensions, just get an extra number to it. So, for directed line segment AB, it's how do I get from A to B? If I look at the x-coordinate, it's negative 1, it's to become 4. So the x-coordinate's got to gain 5, go from negative 1 to 4. The y-coordinate goes from negative 2 to 1, has to gain 3 then, negative 2 gains 3 to become 1. And the z-coordinate is negative 1, it becomes 7, so it has to gain 8. So, for the directed line segment AB, that's going from A to B, you put 5 onto the x-coordinate, 3 onto the y-coordinate, and 8 onto the z-coordinate, and that takes you from A to B. As a column vector, that's 5, 3, 8. X component, y component, z component. Here it is depicted down here. So there's A, give its x-coordinate an extra 5, and it becomes 4. Give the y-coordinate an extra 3, and it becomes 1. Give the z-coordinate an extra 8, and it becomes 7. So to go from A to B, you need to add 5 to the x, 3 to the y, and 8 to the z. That makes the column vector 5, 3, 8. So that's the directed line segment AB in 3 dimensions here. Here's an application of it. Suppose I want to work out the coordinates of D. This is a parallelogram. You've got the coordinates of A, B, and C. When you go from B to C, you go along this red vector here. This vector also is the same vector that takes you from A to D. So whatever BC is, AD is the same. Parallelograms get opposite sides equal, and if we go in the same direction, B to C and A to D, that's going in the same direction, we've got the same vector. So how do you get from B to C? From negative 2 to 1, you must add on 3. To get from 3 to 2, you must take off 1. To get from 5 to 7, you must add on 2. So for the components there, to get from B to C, add 3 onto the x, take 1 off the y, and add 2 onto the z. 3, negative 1, 2 is the vector involved. There it is. To get from B to C, directed line segment BC is the vector 3, negative 1, 2. Since it's a parallelogram, AD is equal to BC. The same size, same direction, same vector. So these two directed line segments are equal. So AD is also the same vector. 3, negative 1, 2. So how do you get from A to D? Add 3 onto the x, take 1 off the y, and put 2 onto the z. So there's A, negative 5, 0, 1. Apply that vector, 3, negative 1, 2. That is, give 3 to the x, take 1 off the y, and add 2 onto the z. And that gives you the coordinates of D. D is negative 2, negative 1, 3. Now you don't need all that working when you do it. You simply need to look at BC and get that vector and apply it to the coordinates of A. So BC takes you from B to C. The same vector takes you from A to D. You have to be careful when you write vectors that you write them as a column and that you don't write them as coordinates like 3, comma, negative 1, comma 2 in brackets like it's coordinates. Don't mix up vectors with coordinates. When you write coordinates, don't write them vertically like a vector. Don't mix them up. A position vector for a point is simply how you get from the origin to that point. So this is point A, 4, 2, 6. How do you get from the origin to A? Well, what you do is you go 4 to the right, 4 onto the x coordinate, 2 onto the y coordinate, 6 onto the z coordinate. So go from the origin to A, 4 on the x, 2 on the y, 6 on the z. So the column vector is 4, 2, 6. Simply, the coordinates 4, 2, 6 have turned into components 4, 2, 6. That's the position vector. So point A has position vector A. The coordinates become components of the vector. Again, don't mix up coordinates with vectors. Now, to show that the magnitude of a vector is simply by squaring components and adding, take the square root. In 2 dimensions, it was done with Pythagoras. It was quite straightforward. It's similar with 3 dimensions. There's how you go from A to B, A on the X, B on the Y, C on the Z from the components here. If you apply Pythagoras here in the bottom, so to get AP squared is A squared plus B squared. That's Pythagoras here. We want the size of AB, so we want in this triangle ABP, we want to get this black line. So AB squared is AP squared plus PB squared. PB is C, and AP squared was A squared plus B squared. So AB squares become A squared plus B squared plus C squared. The components squared and added. So to get AB, you square root that. So simply, AB is the size of the directed line segment AB. So magnitude AB is the same as a line AB. It's just the size of the line. Square the components, add and take the square root. So just like 2 dimensions, but it's got a third component. So there's a general rule. Magnitude of vector U, square the components, add and take the square root. If that's directed line segment AB, you want its size, its magnitude. Square the components, add and take the square root. 9, positive 1 and 4. So that's root 14, won't simplify it. So that's root 14 units is the size of the directed line segment AB, or it's the length of the line AB, or it's the distance between the points A and B. You can add vectors head to tail in 3 dimensions. So if I want AG here, this point A here going to G, I can go along AB, followed by BC, followed by CG. So that's put here as vector U plus V plus W. Any route you go from A to G will be U plus V plus W. So here's a different route. A to E, E to H, and H to G. It's still, there's W plus V plus U. That's the same as U plus V plus W. So it doesn't matter the route, you end up with the same combination of vectors. Here's another case. If you want EC to go from E to C, I can go along here EF, down from F to B, and then from B to C. That's vector U. That's negative W, it's going in the opposite direction to W, and that's V. So it's U minus W plus V. Whatever route you go from E to C, it will always end up with a combination of U, negative W, and V. So these rules, which we're applying to 2 dimensions, are the same rules applying to 3 dimensions. And finally, how to apply it. Get the magnitude of B minus 2A. Simply, as in 2 dimensions, work out B minus 2A first. There's B, there's A. This 2 multiplies the components. 2 times 1, 2 times negative 2, 2 times 3. Subtract now the components. Negative 1 minus 2, 0 minus negative 4, and 2 minus 6. That's B minus 2A. Magnitude of B minus 2A is square the components, add and take the square root. Positive 9, positive 16, positive 16. So remember, square a negative, you get a positive. If you add these up, it's the square root of 41. That doesn't simplify. That's the magnitude of B minus 2A. Work out B minus 2A first, and then use the rule, square the components, add and take the square root. This is exactly as was done in 2 dimensions in previous videos. It's just got a third component there. If you click the link in the description, there's a worksheet. It's the same worksheet used as in the first 2 videos. sorry, it's not, it's the same video, same worksheet as using the last video on coordinates, and following the coordinate questions of the last video, it's got vectors in 3 dimensions, adding them in diagrams head to tail. That was done in 2 dimensions in the third video. Coordinates in 3 dimensions to get directed line segments, working it backwards, using coordinates to get the vector and then the size of the vector, the magnitude, works out the distance between 2 points, applying it here to parallelograms, working with components and getting the magnitude. It has the answers with them. Using the same link, it's a set of notes for all the videos on vectors, covering everything. Hope you found the videos useful.